Okay, let's start the last section in chapter 4. The title of the last section is The Time Dependence of a Function is Governed by the Time-Dependent Schrödinger Equation. So the important keyword is the time-dependent Schrödinger equation. So up to this point, we have focused on the properties of quantum systems at a fixed moment, right? So we have used the time-independent Schrödinger equation. Time-independent. So we cares only about the position of the system. So within the framework of time-independent Schrödinger equation, we can obtain the stationary wave function, psi, and we can obtain the allowed energy levels. But how do these systems actually evolve from one moment to the next? So the answer is governed by our fifth and final postulates. Postulate number 5. So the wave function of a system in time according to the time dependent Schrödinger equation. Evolves. Yeah, I missed the verb. Yeah, the postulate number 5 is the wave function of a system in time evolves according to the time-dependent Schrödinger equation. So the form of the time-dependent Schrödinger equation looks like this. H hat capital psi. So here capital psi denotes the time-dependent wave function. So this contains both variables position x and time t. This should be equal to IH bar, partial derivative of wave function with respect to time t. So this equation is the quantum mechanical equivalent of Newtonian's law of motion. So it is the fundamental rule that dictates the time evolution of any quantum system. Time evolution. So if you try to remember the Newton's second law of motion, that describes the motion of some particle or matter, right? So if you know the initial position and initial some condition, velocity or acceleration, then you can keep track of that particle or matter. But in quantum mechanics, we need time-dependent Schrödinger equation to do the same thing. Okay, so let's talk about the form of the time-dependent Schrödinger equation's solution. So for many systems in chemistry, the Hamiltonian operator H hat. So this does not explicitly depend on time in many cases. So in this common and important case, we can solve the time-dependent Schrödinger equation using a separation of variables technique. So now we are going to separate the large capital psi into the product of a space-only part, small psi x, and the time-only part, ft. So we can perform the separation of variables because the time and space are independent variables. So if you plug in this into the time-dependent Schrödinger equation, I h bar lambda t psi x ft, like this. And as I mentioned, Hamiltonian is usually time independent, which means it only cares about the system's position. So for the operator h hat, time dependent part can be considered as a constant because they don't depend on the position x, so they can go out. And similarly, we are taking the time derivative here. That means the time space only part can go out from this parenthesis. So that means we are going to have some equations like this. And we are going to divide the whole equation by capital psi. The reason why I want to do this is I want to obtain the equation that each side contains only one variable. Let's see this operation can do this. So for the left side, we can remove the time dependent part, and we only have the equation like this. And for the time dependent part, I h bar so if you take a look at the left hand side, the left-hand side contains the x variable, right? There is no time-dependent variable. So, and what about the right-hand side? This part only contains the variable t, right? So there is no x here, t. And when each equation is governed by their own independent variable and they should be equal, that means the only possible way to equate them is they should be some constant e here. So if we take a look at the left hand side, so you may realize that this is the exact form of the time-independent Schrödinger equation. Actually, I have to change the derivative notation here because maybe from here, because this is no more partial differential equation, because we have only one variable due to the separation of variable. This is time-independent Schrödinger equation. And let's take a look at the right-hand side. I h bar over ft and df dt should be equal to e. So this might look a little bit complex, but this is the exact form of the first order linear differential equation. Something like this. So you all know that this ordinary differential equation can be satisfied when we choose the ft as the exponential function. So this is the time-dependent part of the TDSE. Okay, so now we obtain the explicit form of the time-independent part and time-dependent part here. So we want to combine them to obtain the total capital psi. This should be the product of spatial part and time-independent part. So time-independent part should be given as like this. So this is the full time-dependent solution for a single eigenstate. And this is also known as the stationary state. So you might wonder why it is stationary state, because it already contains time-dependent part. So it is related to the probability density. So if we take the square of its magnitude, it should be the multiplication between the wave function's complex conjugate and itself. So as you can easily imagine that, in this magnitude, there is no time-dependent term, because we take the multiplication between the wave function itself and its complex conjugate, so imaginary part will be cancelled out. So that is why we called this wave function is stationary. Its probability density does not really change over time. Okay, so you have to remember that a single eigenstate, this forms a stationary state. There is no probability change over time for a single eigenstate system. Then how does anything ever happen in quantum mechanics? Changes and dynamics occur when a system is in superposition. Okay? So the most general solution to the time-dependent Schrödinger equation is a linear combination of all possible stationary states. So if you want to go a general solution, then it is the linear combination of stationary states. And this is, when I mentioned the superposition, this is mathematically the linear combination of its eigenstate. So that means you want to multiply your full time-dependent Schrödinger equation solution by some constant c, and you want to add up all possible eigenstates. So when we calculate the probability density for this wave function, capital psi, the time-dependent phase factor do not completely cancel for this case, because for the case we discussed above, there is only one eigenvalue, energy E. So when we take the complex conjugate, it exactly cancels out the original form, right? So if it should be given multiplied by something like this. So the time-dependent part should be cancelled out. But for here, there is any term like E1 multiplied by E2, something like this. So energy E1 and E2 can be different. That means this value cannot be cancelled out. Okay, so we are left with time-dependent cross terms. Or interference term. Something like this. And these terms cause the probability density to oscillate and change over time. So let's take a look at the example case. A particle in a box that is prepared in an equal superposition of its first two energy eigenstates. The total wave function capital psi will be given as this is the wave function for n equal 1, and we are going to add the second wave function so the second part is the wave function for n equal 2. So let's take the average position of this particle. So the average position of this system is simply the expectation value, and you can calculate the expectation value by sandwiching the operator x hat between the wave function and its complex conjugate, like this. And it should be quite long mathematical expression, so you want to plug this into here and here, and you want to calculate the expectation value. And I don't want to follow all the details, but let's take a look at the final results. And it should be given like so as you can see here, when you calculate the expectation value for the position x within the time-independent framework, we expect that the expectation value should be a hat, exactly center of the box. But when we consider the extra term, time-dependent term here, this one and this one, you can see that there is an extra term here. We are not going to really discuss this constant, but we have to understand this term. So as you can see here, there is a time dependency here. Time variable t appears here, and its form is cosine function. That means that as time evolves, the expectation value of position x will change over time too. And how fast it oscillates, it is determined by the energy difference between two eigenstates. So omega 1, 2, this is simply the energy difference between two eigenstates divided by the reduced Planck constant. So if you have a two system that has very similar energies, that means the omega value should be very, very small. Then the oscillation between two states might be very slow. But what about the system with a large energy difference? That means the omega value also should be very large. That means the oscillation between the first and second eigenstate should be very, very fast. So it is the very important results that the dynamics and transition are governed by its energy difference. So it is all about the theoretical basis for all forms of spectroscopy. So even though this is very simple and basic examples, but it is a very fundamental issue. Okay, this is the end of the chapter 4. So if you want to know more about the time-dependent part, and please read the textbook by yourself. And there is some additional content about the evolution over average value and constant of motion, but this is a little bit beyond our scope. So we want to focus on time-independent part in undergraduate quantum chemistry lecture. Okay.